Great. I hope that you had time to go through most of the notebook. This was a bit shorter still. I mean, there's plenty of materials in here. Just to be sure, can you hear me and do you see my Jupyter notebook? Yes, super. Thank you, guys. And we also have Anas online. Hi, Anas.
Yep.
Great to have you.
Yeah.
So I guess that most of you were able to do half or at least half of the notebook. Is that the case? Yeah. Super. Good job, guys. And again, the notebook will be available online, and we'll also put the videos with these discussions and presentation of the dataset and discussion. So you have a lot of time to go back and see the things that you missed the first time. So we already described the dataset. I will quickly go through the data. And here, one of the big things, so just for sake of clarity, well, I'll quickly describe again the dataset. The dataset consists of protein sequences from different organisms that grow at different temperatures. And our goal here is to understand if there is any specific feature in the proteins that grow at higher or lower temperature, in the proteins from organisms that live at higher or lower temperature that can be found in the data. And one of the technical learning objectives for this module is the use of NumPy. Together with Pandas, NumPy is one of the pillars in data science with Python. It's a numeric library. It's very much optimized for speed. It's using some kind of tricks because basically NumPy has a lot of functions that are built or compiled in other languages such as C and C++ to make it efficient for speed. It's a numeric library, so it's basically only deals with numbers, but it's very useful also when you have to deal with a large amount of a large data set of protein sequences. Let's go through the import. Again, run everything. Remember to run everything, otherwise things might not work. Loading the data. And we see that the data that we have just loaded, it's a NumPy ND array. We can get a look and we see that the data are sequences, but they are encoded as numbers. So this is a kind of a naive way to translate sequences into numbers in a way in which each amino acid, we have 20 amino acids, each one is defined by a specific number. So for example, here we have 11199, and that's going to correspond to a specific sequence, right? And 28 is the growth temperature corresponding to that specific sequence, 28 Celsius. And we got that the shape for the X data, it's 10,000 proteins, 650 columns, and the shape for Y, the Y variable is 10,000. Again, the Y data contains the growth temperature. Now, first question is, what is the maximum length for each protein in the data set? A naive way to do that, it's just write the size of the data set, right? 650. Now, if you look at the data, you can see that in many cases, some of the proteins are shorter than that. So at the end of the sequence, they contain only zeros. This trick is called padding. Basically, in order to have sequences all of the same length, you include zeros to make things even. And this is something that it's extremely common in data science, especially when you need to do machine learning. Machine learning algorithms like to have inputs that are the same size, and with sequences, that's simply not the case, right? So either you compress the sequence in a way that, for example, you describe the sequence only by its amino acid composition, so you only describe the sequence with 20 numbers, or you need to do so that the sequences have the same length. And nothing. I think here it's pretty basic things. You can still slice things using the same way that we were using in pandas. So for example, if you want to have a look at the first two amino acids, you go from 0 to 2. So position 0 and 1. Remember that the last number is not included. And you have something like this. You can also do casting, meaning that you can transform NumPy objects to pandas and the other way around. And this is something that's extremely common in Python. So for example, if you want to write the describe function, you just use the pandas function here. PD stands for pandas. When you import it to the library up here, you see that we imported pandas with the short name PD. So whenever we are writing PD, we're referring to functions that are coming from the pandas library. Whenever we write NP, we refer to functions library. So going back, by doing like this, we are converting the NumPy object. The NumPy object, we are converting it to a NumPy data frame, and then we're using describe. Here it comes, and you see that you have count of how many samples you have in each column, the mean, standard deviation. Now, as you see, since those are not numbers, but they are amino acid, it doesn't make sense to calculate the mean in this kind of statistics. So what you can do is that you can force the amino acid to a different type. So we don't want to treat them as numbers, but as strings. And then you get something like this, statistics that are more meaningful. So for example, in the column 0, you have 13 unique values, meaning you have 13 different amino acids over the 10,000 proteins. And the amino acid that is most common is amino acid number 11. And so on and so forth until the end. I think here we can scan through everything. So for example, how many unique amino acids are found in the first position of all proteins in the data set? We've seen that there is 13 of them. Now, if we want to go back from this encoding that we are using in order to show things in NumPy to real sequences, we can use one of the Python native type of variables that are dictionaries. This kind of data is quite common in all the programming languages, but the basic idea is that you assign a value to a set of values to a set of key in a one-to-one relationship, meaning that you assign a single value to each key. Now, if you go through the notebook, there are a few other things that are explained. I will not spend a lot of time going through these. But here you can see that how you can create dictionaries and access value from the dictionaries, how you can actually use the zip function to combine lists or tuples into a single object that can be iterated, that they can be used in a for loop. So now from 2 lists, we got a single one in which each element contains something from the first list and something from the second. So A1, B2, C3. And then when we iterate, we can iterate on both things together in this way. So we can create a dictionary that assigns to the numbers the corresponding letter. Now, this is a very Pythonic way to do things. So you will see these over and over when you look at Python code, right? For example, to the number 19, its corresponding amino acid is tryptophan. Here. And as if you know a little bit about proteins, you know that at the beginning of proteins, very often we see methionines because they are corresponding to the starting side of our translation. And amino acid 11 actually corresponds to methionine. So that makes sense. Let's move forward. We have here another thing that is kind of fundamental in Python, writing small functions. Here we describe a small function that can convert a sequence of numbers to a sequence of amino acids. And you can use that. You see, this is the translation of the first row in the NumPy array, and this is the actual sequence that is encoded by that row. There's many ways to do the same. There's a small question here. You have a small peptide encoded in this way. And what you can do is that you can decode the peptide. And you see here that you get a peptide that is BioDataSience. Now, a little bit of playing around with these kind of basic tools. You can extract the first 10 amino acids of the first 1,000 proteins. You can write them with a very few lines, and you can write them as a TXT file, or you can use Pickle to directly save the object. So, what is the difference here? Sometimes you have a very large data set that you have saved, and you don't want to save it as a CSV or TXT file. And then when you open, you need again to use pandas, for example, to load the data into some variable, into some data frame. Using Pickle, you can directly save the object, the data frame, the variable, the list. When you load the object, it will be directly loaded into a variable. So that's a nice things that you can do with Pickle. Okay, let's go to the scientifically interesting part. Optimal growth temperature. We see that if now we do some statistics over it, we see that there is a mean growth temperature of 34.7 Celsius with a standard deviation of 12, but with a range that it's very large. So it's between 4 degrees Celsius and 103. Let's try to plot this using Seaborn. We get something like this. Now, as you can see, the original data is the one that it's plotted with these bars in cyan, and we also kind of can make an estimate of the distribution, probability distribution that it's in the back of this data. So what is the real probability distribution? Great. So you see that the probability distribution is kind of smoother here than the original data. And this is done directly by Seaborn using this parameter that it's BW equal to. That basically it's using a running window to smooth things out. So if we use 1 instead, we'll see that the distribution that is estimated with the line, it's much more rough, right? If we use a larger window here, we'll see distributions that are much smoother. Now, this here is done in a very naive way, but the problem of estimating distribution from a discrete or a small set of data points, it's of extreme importance in data science, and it's something that you will do all over in your work life, right? So for what I do, for example, it's extremely important in machine learning. When you train a machine learning algorithm, what you actually are doing is that you are learning distributions for a small data set, and you want that this probability distribution generalized, meaning that they are meaningful even outside of the data that you have used to train. And again, I think that here this is a big thing also in Bayesian statistics. So I might leave the the word here to Anas if he has something to add.
About estimating probability distributions?
Yeah.
Yeah, so I mean, obviously, there's always the case that we have limited data and we want to infer something general. That is at the heart of a lot of what we're doing. Kernel methods is one way. I mean, if you have some sort of meaningful prior knowledge, then that is of course useful to take into account. In the Bayesian world, again, we would have a prior maybe for some, but in cases like this where you're discovering stuff, I mean, I have no idea what the real distribution of growth temperatures are out in the wild. So we sort of have to just see what the data is telling us here. And there's no easy way to know if this is a representative sample of all species or what that even means.
Yep. Great. So let's move forward. The cool thing is that here you can extract directly data points from the plot. So you can go both ways, plotting the data and getting numbers from the plot. You can do this with these functions. Let's play around. You can sort. I mean, you have all the numbers now. And you see, if now we plot, we have extracted the value of this interpolation line and plotted it again. So we kind of were able to retrieve only the background function.
Maybe one point I'm just thinking of now is that if you do know something about the expected distribution, then you can use that to sanity check your data set. I mean, this is what you do in polling, for instance, right? If you want to know who gets, whether Donald Trump wins the election or not, and you poll 1,500 people from across the USA, then you can check the distribution of various demographics and see if that fits with what you sort of know that that distribution should be. And if it doesn't fit, then you know that your data set is biased and you need to correct for that. And you can then actually correct for it by squeezing it to be more like the known demographic distribution. So you can do that in data science contexts also.
Yep, very good point. So yeah, we still have a little bit of time, so maybe here we can move forward. Again, this is about the temperature. And similar things about the sequence length. So we don't know, maybe the sequence length is what really matters for in terms of thermostability of proteins, right? So we have a little bit of Python magic, and here we plot the distribution of the sequence length, and we see that we have a distribution that is kind of meaningful. We have short proteins that are 50-ish amino acid. We have long proteins of 600. In general, bacterial proteins might be a little bit longer than these, but this is a kind of a fair data set of protein lengths, right? And we have a peak that it's between 300 and 400, around 300. This also makes sense. This is what we expect to see. Again, at this stage, do a lot of plotting, do a lot of statistics, because you really need to see your data. For example, here, I mean, we can understand here that there is a small bias. We have kind of excluded very long proteins that are more than 1,000 amino acids. Now, this might be useful because they are not so many, and we don't want to focus on this kind of long proteins, but we need to know that, right? So plotting and exploring the data is a fundamental thing in when you start and try to perform some kind of task. And here it's explaining a little bit how you can do this kind of histograms and bar plots. I think there's not much to tell here. So yeah, okay. I will skip this and I'll go to parts that are a little bit more interesting for us. Again, correlations. Now we are plotting a correlation between sequence length and the temperature. It's a scatter plot here, so each dot corresponds to protein. On the x-axis, we have the length of the protein. On the y-axis, we have the growth temperature for the organism that is expressing the protein. What we see here is that basically there is no correlation. We see that the blue line, that it's the regression line, is basically flat, and we can see that the dots are all over the place. So we can see from this visual inspection that there is actually no connection between the sequence length and the thermal stability. So now I lost track. What was the okay, Pearson R. Yes. So the name of the variables here is, let me see, lengths and y data. I'm using a small trick here. We didn't explain it before. In general, in the notebooks, if you press tab while you're writing something, it will give you suggestions or autocomplete things. So if you, as I am, forget immediately the name of the variables, this is really, really helpful. Okay, here it is. And this is something that I think it's interesting. We see a Pearson correlation between the length and the temperature of -0.04 and the p-value. Sorry, Anna, I told the p-word. And the p-value is 5.1 to the -6, so it's highly significant. And I think this is something that people should be aware. Significance does not, statistical significance does not equate to biological significance. I don't know if Hannes wants to take.
I absolutely do.
No. I knew that.
No, I could go on for an hour. No, but I mean, just looking at that plot, I think it's pretty obvious that, so the correlation is uninteresting biologically, and even the fact that there is a correlation is meaningless, because the thing about p-values is that if you have it's telling you whether something is, that's the nature of null hypothesis testing, at least typically. You're testing whether something is exactly equal to 0, okay? And I mean, in the biological world, nothing is, or in any scientific field really, you're almost never investigating hypotheses where something is exactly equal to 0. So if you have enough data points like we do here, it will be highly significant, but that is mostly a function of the number of samples. So with enough, with several thousand data points or millions if we have in genomics, anything can be significant as long as it's not exactly 0. And I'm telling you, it will never be exactly 0. Yeah. So the p-value is telling you very little of interest.
Yeah, and I agree completely. This is also true for machine learning, right? So you see a p-value and you think, okay, great. Then there is a signal in the data that I can exploit to do a prediction. And then this p-value, it's on a difference that it's so small that practically you get so many false positives or false negatives that the prediction that you're doing is completely unuseful. If we look at these and we say, okay, we want to find a cutoff in the sequence length so that sequences that are longer than 400 grow at lower temperature than sequences that are shorter than 400. You can see clearly that it doesn't make sense. You have things all over the place. There is a significant statistical significance. There is no signal to train any kind of predictor. Great, so let's move forward. Great. Now, let's move forward and let's analyze amino acid frequency. So the idea here is that, okay, maybe the difference in the thermostable and not thermostable proteins is in the amino acid compositions. And this is kind of the running hypothesis that people have. But it's not so straightforward, as we will see. We have to run a little bit of things here to make some magic. And we are visualizing here the overall distribution of amino acids. Maybe I should run it again. Here it is, sorry. This is called a swarm plot, and it's, I don't know, I like it very much. It's, again, as for the volume plot, it's a nice way to explore the data. It gives you a feeling of where the average is, but also of the kind of distribution that you observe. I don't know, it's very pleasing to the eye for me. As we can see here, we have amino acids that are more frequent as alanine, leucine, serine, and we have amino acids that are more rare, such as tryptophan or histidine or cysteine. Now this is what it's pretty much expected. What we can do is that we can split up things in different classes and compare the distribution in organisms that grow at low temperature, at middle temperature, and high temperature. These are the distribution of the temperatures, and we can use this to split things up in three. In this case, we have decided to use less than 20 degrees, between 20 and 45, and more than 45. We split up things. We do some statistics over these, and we calculate the amino acid content in the three groups. For example, for thermophiles, we have something that looks like this. And we have an average length of 280 amino acids. And here we have the frequency of amino acids from the most common to the least common in the thermophiles. Now, if we plot all of these together, we get something like this. So in yellow, you have the organisms that grow nicely at average temperature. In blue, the ones that grow at low temperature. In red, the ones that grow at high temperature. And we can see some differences. I would say that this plot, even though it's quite good, I don't think that it's a nice way to see the difference between the data sets, right? So I would say that you have a few problems here. That, I mean, the bars overlap one with each other, so it's not really possible to compare them easily. And also, what we are counting on the y-axis is this frequency that might not be the most important things to study, to analyze, right? So we can actually choose a different approach. I'll just skim through things. And for example, compare thermophiles and cryophiles, one next to the other. Now here, things are a little bit easier to compare. We can, for example, see that arginine here is underexpressed or underpresent in cryophiles, and for example that asparagine is overexpressed. And we can see also for thermophiles that, for example, alanine is underexpressed, and lysine here, it's overexpressed. So this is a better way to see differences. And this is kind of a very important tool whenever visualizing protein content, but also when visualizing the so-called protein logos. So in general, here we see things that are overexpressed and underexpressed. But for example, we know that in general, serines are much more common than, say, methionines or tryptophans, right? So a small change in tryptophans might be more significant than a large change in serines or leucines. This is why, in general, you don't use counts or you don't use frequency to visualize these kind of things, but you use other measures. And one of the most typical is Shannon entropy, that it's the information content that you have for that specific amino acid. Or even better, you want to compare the frequency of amino acids in a given data set with a background distribution of, for example, frequency of amino acids on average. And in that case, you would use something that is called the Kalbeck-Leibler divergence measure. Now, we'll not go into a lot of details here about this, but we've kind of tried to analyze here in a few lines which kind of feature we can extract and visualize in a data set. Consider that the data set here that you have been using is 10,000 proteins, but using NumPy, you can actually analyze very, very large data sets. Okay, Magnus is reminding me the full data set that you have here is actually almost 8 million sequences. So this is something that, of course, you really need Python or some kind of programming language in order to be able to analyze this kind of large data sets. Great. So I think I'm finished. I don't know, Hannes, if you have other.
Maybe just one technical statistical comment with respect to this. So I think this plot is quite nice. There's one problem generally if we're interested in looking at data like this, which are that they are compositional, meaning that the percentage of the amino acids have to sum up to 100%, because I mean that's how it is, of course. So the thing is that if you're comparing two groups of sequences, and imagine that if one amino acid goes down, imagine that the main effect, for instance, is that we no longer want arginine in our proteins. Then if we remove arginine completely from all our proteins in the thermophile group or whatever, then the frequency, and don't change anything about the rest, then all the other frequencies have to go up. So there are some complicated things happen, and that would seem if you just compared frequencies of, say, alanine in thermophiles versus frequencies of alanines in non-thermophiles, it would look as if alanine was over represented, but it's really just because something else disappeared. That is a problem with this kind of data, and I'm doing some research actually on this type of thing, and one way around it is to instead look at ratios between amino acids. So using some one of the amino acids as the base, and then taking the ratio of all the rest towards that. And there are even more nifty ways of doing it, where you do some log ratios, but that's going too far. I'm just mentioning it as a thing that you get these. If you remove something and it has to sum to 100%, then the rest will go up, even though you haven't actually changed it.
Yeah, it's actually a great point. I mean, they are all descriptions of the same data set. So if you use Shannon entropy, for example, to describe the changes, you will see that amino acids are all over the place, let's say. So you see a lot of amino acids that are regulated, let's say. If you use the KL divergence, so if you normalize by the background, you will see that, for example, in this case, the arginine would be negatively on the negative side because it's underexpressed, and all the other amino acids will be slightly up. And if you use the approach that you are suggesting, or there is also another method that is doing the same, actually you would like to have a model or an explanation that it's only telling you that you can explain everything by the under representation of arginine. And yeah, I mean, in general, it's a good point that data and visualization tools, you always have to understand what you're really seeing, right? So for example, it might not be meaningful here to say that methionine is overexpressed, because probably this is just a side effect of underexpression of arginine. Now we are almost out of time. I would like to get questions if you have. Of course, you're also welcome to send us questions by email later on. Great. If there's no question, what I want to remind you is that, first of all, the notebooks will be available for 1 more week. Second, we'll send a follow-up email to send you all the materials and all the links, but also we'll kindly ask you to take part of a small feedback survey. We really appreciate your feedback. If you liked the webinar, share it with your friends and give us a thumb up, because it's really important for us. If you didn't like it, tell us why, and we'll try to improve for our next event. And that being said, I want to thank you all for taking part to our first webinar. It's been a pleasure for me. It's been incredibly, it's exhausting to prepare everything, but also I'm very happy of how things went. And I hope to see you all soon, possibly in a live event. Thank you all. Thank you, Hannes.
Yep. Bye. Thank you all. Also.
Great. See you. Bye-bye.